The original design goals of my Astronomer's Compass project have been met. I recently thought of a few new ideas to include, but since this video is way overdue, I'll show you what I've got and make this a progress report. The hardware is complete. Everything works, but calibration is not done, and it should be if the compass is to have reasonable accuracy. Calibration needs to include sensor calibration, but maybe even star or polar alignment. Nonetheless, I've got to figure out calibration, but rather than delay the video further, I'm putting it out with the functionality that the compass has to date. Let me take you on a quick tour through the compass functions that are present, some of which should seem familiar from months ago, but this time with live data, putting a shine on the apple. You've seen this page before, but this time there's live data from GPS. Locating objects in the night sky depends in part on knowing where we are on Earth. Our location is given as latitude and longitude, measured in degrees and minutes. The time zone sets the relationship between local time and coordinated universal time. GPS doesn't do time zones. I've got to set this manually. However, GPS does provide the solar date and coordinated universal time. I use these and the time zone to calculate local time and sidereal time. Azimuth is the compass heading given in degrees and minutes from north, where north is 0 degrees, east is 90 degrees, and so on. Looking up into the sky, there's also a vertical component, altitude, that measures an angle above the horizon. For both azimuth and altitude, degrees are divided into minutes for higher resolution. Whether that resolution is practical, we'll leave for later. If we look, say, southwest and up into the sky, this direction is roughly 225 degrees azimuth and 45 degrees altitude. This measurement comes directly from the orientation sensor. However, the goal of the astronomer's compass is to show direction in terms of celestial coordinates known as right ascension and declination. And this is the page that shows that. These values are calculated from azimuth and altitude from the orientation sensor, and the position data and time from the GPS. So all of these values come together to reveal that we're looking at 14 hours, 31 minutes, right ascension, and 6 degrees 10 minutes declination. Whatever direction my compass points, this page shows the celestial coordinates of that direction for that moment in time. Actually, for this moment in time, because all the data here is live at 8:34 p.m. Another new feature since the previous video, I've built a catalog into the astronomer's compass, in which I keep a collection of selected deep sky targets. I chose objects for the catalog based on monthly suggestions from YouTube astronomy channels like Alan Wallace, email newsletters from retailers like High Point Scientific, and independent websites like Telescopius, and suggestions found in some popular books and other sources. I used Astroplaner to assemble the target suggestions into a personalized quarterly observing list. I exported the list, I reformatted it to binary to compact it, and I indexed it, and I downloaded the result to a double EEPROM using a CH341 double EEPROM programmer. In short, my catalog is a compilation made up of excerpts from standard catalogs. It's even indexed by standard catalog designations. Among the targets I have stars, constellations, and nebulae. They all came from selections in my Astroplaner observing list. For example, M12 is the Messier catalog designation for the Gumball cluster. Information about the target includes properties such as its magnitude, its size, its type, and its home constellation, plus aliases and cross-references to other catalogs like the NGC catalog. An identifying property of any deep sky object is its position in the sky. M12 coordinates are right ascension 16 hours 47 minutes and declination -1 degree 57 minutes. To find M12 in the sky, well, it's already selected as the target. We saw this page earlier. It's the line of sight given in terms of celestial coordinates. This time the target coordinates also appear on the page. To find the target in the sky, it's a matter of aiming to match the coordinates. I added an audible cue to help find the target. With it, I can keep my eye to the eyepiece while hunting for the target and have some indication whether I'm hot or cold. So what about calibration? Stars won't show up in the video, but the moon will be a much better target to get a measure of just how far off the uncalibrated compass measurements are. In preparation of shooting the moon, I made a sighting tube from a drinking straw. It'll be visible in the video as I take aim. And this is what I saw. What looks like Saturn slipping out of its rings is the moon seen through the straw, the reflected light creating a deformed ring. That's Jupiter up and to the right of the moon. Here, what looks like a full moon is an out-of-focus half moon. This morning at 4:49, the moon was really at 113 degrees azimuth, 54 degrees altitude, according to Astronomer. The celestial coordinates don't matter because they're calculated from azimuth and altitude. Calibrating azimuth and altitude will carry over to celestial coordinates. The compass says the bearing to the moon is 125 degrees. That's the magnetic bearing. Around here, the magnetic declination is about -10 degrees, so the true bearing is 115 degrees, roughly a 2-degree error. What we don't know is whether it's constant around the full circle or not. There's also a 1 or 2 degree error in altitude as well. This was a very crude test, but to tell the truth, I'm more than a little pleased that it came out as close as it did. But there's still more to do for calibration. Actually, there's everything to do for calibration. The OLED display, the piezoelectric speaker, the encoder, and the push button combine to make up the user interface. The astronomer's compass can operate in live mode or manual mode. In live mode, data is periodically gathered from the GPS and the orientation sensors and displayed on the OLED. In manual mode, data is not gathered from the sensors. A single push of the push button activates manual mode and focuses on one of the on-screen values. The focused data is highlighted and the encoder can adjust the value. Each following single push on the button advances focus to the next adjustable value. Each focused item can be adjusted by the encoder. After the last value, focus is said to be on the page, where the encoder can select the next page or the previous page. Again, while in manual mode, the sensors don't contribute to displayed values. So changing the line of sight has no effect on displayed values. Even the real-time clock is in effect disconnected. The whole point of manual mode is to be able to set any location, date, time, azimuth, or altitude, and see the resulting right ascension and declination. In other words, the compass becomes a calculator. To re-engage the sensors, a long push returns to live mode. The audible proximity indicator we heard earlier is also part of the user interface. It's enabled by a double push, but only activates under certain conditions. Chief among them is that the compass points close to the target. Another double push, or a single push into manual mode, toggles it off. The list of modules that make the astronomer's compass possible begins with the GPS module. This module provides the location data. As a bonus, it also provides coordinated universal time, eliminating the need for a single-function real-time clock. GPS is free-running. providing a continuous stream of data, and the Nano can just listen without soliciting the data. Once they plant their equipment, astronomers tend to stay in one place for an entire night while observing, so the GPS sensor doesn't change. It can be monitored rather casually, and practical use of the compass won't require more than arc-minute precision for the location. With minute resolution, there's no need to check the time more than once every 30 seconds. The compass, however, checks every 15 seconds, but only so that the time doesn't lag too far behind other clocks. The azimuth and altitude values are measured by the Adafruit B&O 055 Absolute Orientation Sensor. It's likely that the platform for the compass won't be stable enough for arc-minute resolution to be appropriate, even though the sensor measures to the arc-second. This is freehand, and I'm trying to acquire and hold 150 degrees azimuth and 40 degrees altitude, and I'm just not able to. Even on a tripod or attached to a Dobsonian telescope, the tripod, or scope, would likely be hand-operated. Arc-minute precision would be optimistic. Arc-second resolution would be pointless. It might be more reasonable to have quarter-degree or half-degree resolution, but my compass will remain optimistic and maintain and display arc-minute resolution for altitude and azimuth. Same for RA and declination. While we're at it, we'll use arc-minute resolution for GPS coordinates and use minute resolution for coordinated universal time. The built-in catalog that I demonstrated earlier is stored in one of these EEPROM modules, but I replaced the 32K byte integrated circuit with an 8K byte version. I keep 4 seasonal catalogs. This one for June, July, and August contains about 50 objects, which occupy half of one 8K byte EEPROM. It's easily expandable back to 32K bytes, but I'm comfortable with the current size. I don't need an exhaustive catalog. I built this catalog from objects that interest me. The GPS module determines where the astrocompass is located on Earth and what time it is. The B&O 055 provides information about the heading and pitch, the orientation of the compass. The EEPROM stores the catalog of celestial objects. The OLED display, the encoder, the push-button switch, and the piezoelectric speaker collectively make up the user interface. The LS18 integrated circuit debounces the pulses from the encoder and the push-button. There's also a voltage regulator to cut down 9 volts from the battery to 5 volts. The current draw from the battery fluctuates around 110 milliamps. And of course, there's the Nano. From the start, I built the Astronomer's compass to run on the Nano. There are bigger, better, faster alternatives, but I have several Nanos that I want to use up, and so far the Nano has been adequate for the job. Here's a summary of the Nano's resources that the project uses. The program, the font, and the title page graphic use slightly more than half the available flash memory. The program heap stores the majority of the compass's data and uses half the available RAM. The other half is occupied by the stack. How much, I don't know, but it should be within safe limits. There's 1K of built-in EEPROM, which for now is unused, but I may put calibration parameters there when I address calibration. The Nano has 3 timers, and the compass uses all 3. Timer 0 is used as a delay timer, although it's non-blocking. Timer 1 distinguishes among the types of button pushes. Timer 2 generates the audio tones for the piezoelectric speaker. The OLED display, EEPROM module, and the orientation module all share the TWI bus to connect to the Nano. The GPS module connects to the Nano too, but uses the UART serial port. The GPS module spontaneously sends data over this connection, so it doesn't need prompting, and the Nano doesn't need the outbound half of the serial port. Besides the TWI and serial pins, 4 GPIO pins are used. The push button uses the input capture pin. Pin 4 connects to the encoder data pin, and the interrupt to 0 pin is pulled low by the encoder clock pin. The only output GPIO pin is the output compare pin 2A. Pulses output to this pin drive the piezoelectric speaker. The compass handles 6 interrupts. Interrupt 0, of course, is the nano's trigger to read the encoder data. By handling the TWI interrupt, the OLED, BNO055, and the double EEPROM are handled by default. The receive side of the USART has an interrupt. It's enabled every 15 seconds to listen for GPS. Timer 0 is used for delay functions. The delays are non-blocking, just like in all those videos that demonstrate the millis function. It marks the passage of time with the output compare interrupt. Timer 1 handles push-button presses using 2 interrupt services. The input capture interrupt starts the timer and separates a double push from a single push. The overflow interrupt distinguishes a short press from a long press of the push button. There's no interrupt service associated with Timer 2. Timer 2 generates a pulse train of varying frequency to produce sound at the piezo speaker. The CPU turns on the timer and turns it off, and in between feeds a varying waveform to the timer on the fly. Other than that, the timer is free running. The CPU doesn't need to maintain the pulse train or have any interaction with the timer except to change the wave period. So there's no interrupt associated with Timer 2. I mentioned earlier that there are a few pending features that I postponed in order to get this video out. I mention them here because I intend to implement them, and soon. The first is the ability to redefine the orientation axes. Throughout this video, the astronomer's compass heading has been defined as where the primary axis points, as shown by the arrow. Here it points north. Let's say a target lies eastward and upward. It can be awkward to read the display, even on a tripod, even on a full-size tripod. On my to-do list is a feature that will allow the primary axis to be realigned so that it might be rotated 180 degrees. Pointing the compass towards our eastern target, the compass is much easier to read. Even on a tripod. Except in daylight. This orientation would be well suited to a Newtonian or a Dob, allowing the display to be read easily when sitting or standing at the eyepiece. The BNO055 measures elevation from gravitational effects. Those measurements should be calibrated, but nearby objects shouldn't have any effect on it. My biggest remaining challenge is magnetic calibration. The BNO055 measures azimuth magnetically, so it can be affected by nearby ferrous material, such as steel telescopes, binoculars, mounts, and tripods. In theory, these effects can be calibrated away, but I haven't yet worked out how. The calibration methods I've tried basically tumble the orientation sensor full circle around each degree of freedom. If the calibration is to account for the magnetic effect of my telescope, doesn't the telescope have to tumble right along with the compass? This is easy enough for the compass alone, but how do I tumble the compass if it's attached to a 12-inch Dob? However, there's this. The compass is facing roughly east and is responding to movement from side to side. That's a magnet descending over the compass and circling around. Why isn't the compass going crazy at the moment? I expect to see some chaotic disorientation of the compass. The magnet just got caught on the battery. It's puzzling to me that there's no reaction. But the compass still responds to changes in direction. Still within the issue of calibration, there's also polar alignment or star alignment. I don't know what kind of ritual will be involved for that, but it'll probably have to correct, for example, the diverging line of sight that can occur between the compass and the optical device, here exaggerated to make a point. I really want to resolve calibration to have the sensor perform well, because with this sensor, the astronomer's compass doesn't need to be tethered to any kind of base platform, no mechanical gears, cables, linkages, or encoders, and I can mount it onto a small telescope, or onto an ordinary camera tripod, or just hold it freehand. Meade and Orion have their push-to Dobsonian telescopes. So do I. And I have a push-to binocular. I even have a push-to soda straw. Well, that's it for now. The work continues. Thanks for your patience, and thanks for watching.